class. Okay, so we're going to talk about a couple things in this lecture. Current density, and something called the Druid Model. So we're going to start out by defining current. And basically a current is a flow of electric charge. So right now, let's say we have a wire here. And say we look at a cross section of this wire. So we have this surface with an area A. A would be the cross section area of that wire. And we're going to define current as the rate that charge passes that surface. So, rate dq dt. Q is charge. We take the derivative. That's the rate that charge is passing through this surface. And that's how we define current. And, we want to kind of visualize what's actually going on inside this wire. And there's a couple ways we can visualize what's happening inside the wire. We're going to look at two models. One is kind of a ridiculous model where let's say that we have charges that are doing this. All right, let's just so let's picture these charges that are all moving, just along the wire. So they're all moving in the direction of the wire. And say they're all moving at the same speed v. So we have all these equal charges moving with this speed v. And this is a very primitive model of a current and not what's actually going on inside like a metal conducting wire. However, currents are more general than just what's going on inside a wire. So if you had a situation like this, this definition of current would work just fine. But this is kind of our easiest model for an electric current. Just nice, everything's moving the same speed in the same direction. Now we do have one little issue though. When we're looking at charges, there's two types of charges. We have positive and negative charges. And obviously, positive charges moving to the right, that's carrying positive charge in the direction to the right. Where we have negative charges moving to the right, that's very different. And so we define current to be, we define it in a way, current has a direction. And that is the direction that positive charge is being carried. So if we had positive charges moving to the right, that would be a current to the right. Now, if we have a current to the right, if it's negative charges that are moving, then the negative charges would have to be moving to the left. And it's kind of unfortunate that it worked out this way. And this goes all the way back to Benjamin Franklin. So if you remember how we first learned about electricity, it's from friction. You rub things together and they transfer charge. And Ben Franklin is the one who came up with the terms positive and negative. It was Charles Dufay discovered that there's two types of charges, but it was Ben Franklin that gave them the names, positive and negative. And I don't even know the history of how he chose one over the other, but basically, you rub two materials, you just pick one of them, say this is positive, the other is negative. Not sure which materials, or even if he had any reason. I don't think he had a reason for picking one material over the other. And it turned out to be very unfortunate that he picked things the way that they did, though, because we're going to learn that in conductors, the overwhelming majority of cases where we're talking about electrical currents, we're talking about inside a metal conducting material. And in that case, it is electrons that are moving. And so if you have a wire and say you have a current to the right, it's actually the electrons moving to the left in this case. So now there are cases where we can have like a positive charge flowing that creates a current. Like inside a battery, there can be chemical like ions, like positively charged ions that move. And yeah, that would be a direction, that'd be a current in the direction it's moving. Like semiconductors, you can have positive charges moving. But mostly things are going the opposite direction as the current. In the most common cases we look at. However, we're going to look in a little more detail about what's going on inside a conductor. And again, inside a conductor, it doesn't mean that the electrons are all moving to the left. It just, some are moving to the right, some are moving to the left. But we're going to have more motion to the left. So we'll get into that in a little more detail later on. So right now, we're going to focus on this very primitive model where everything behaves nicely. Moving at a constant speed. And let's just pick some time interval delta t. It could be a finite time interval. Doesn't even matter in this case because everything's moving with the same constant velocity. And let's pick in some time interval delta t. Let's look at each charge is going to move a distance v delta t. And so if we look at this distance here, v delta t, we're going to draw another charge. It's like this charge here is going to pass through that surface in a time v delta t. I'm going to move this one over a tiny bit. It's like how many charges are going to pass through that surface in the time delta t. We can look at this cylinder here. And everything inside this cylinder is going to pass through that surface in the time interval delta t. They're all going to move over this amount. So this one's going to end up over here. This one's going to end up a little past the surface. This one's going to end up here. It's not going to cross the right end of this cylinder. And so we can say the total charge that passes the surface, let's call that delta Q, that'd be the number of charges times Q. Q is the charge of a single moving particle. So we have to find out, how many charges are crossing that surface. And we can write it this way. Where, see, we've got two V's in this problem. Here is velocity. This capital V is volume. So I'm writing that in a distinct way, so we don't make any confusion about that. So V is the volume of this cylinder. N is the number density. So this would be like the number of particles per cubic centimeter, for example. So N is number density. Let's write that down. I've got this thing for copper. We're going to use that later. So N is number density. It would be like particles per cubic centimeter, for example. All right, and so that'd be like a property of this material. And the volume would be V delta T times A. We have a nice cylindrical wire, cross-section A, the length of that cylinder is V delta T. So this would be N V delta T A times Q. And again, this is a capital V for volume. This is the velocity that those charges are moving. And then the current is delta Q over delta T. So we just divide this by delta T, and we get N, I'm going to write it this way. So we have NQV. Sorry, let me do it. NQA. That's that part times V. We divide it by delta T. And so this is the current, NQA times V, where V is the velocity that these charges, so Q is the charge, V is the velocity that they are moving. And we're going to find one more thing. So here we have current. In general, it's dq dt. And we're going to find something else called current density. We use the letter J for that. That's a current over the area. So if we divide the current by the area, we get the current density is just NQV. All right, now these results, I'm going to write them on the side, maybe not on our, yeah, we'll write them here. So current and current density is NQ times V. So V is the speed of that these moving charges, or that the charges are moving. And right now we're considering this kind of ridiculous model. They're all just moving the same speed in a nice uniform way. All right, now we're going to look at an actual conductor. Like, say we want to know the velocity of, like, the what's going on inside a conductor. We're going to stick with this very simple model for now, and that's why copper is the most common type of conductor that we use. Copper and aluminum are both very common, and let's try to get some estimate for the velocity of the moving charges inside, say, a copper wire. So, problem here, say we have a copper wire with a diameter (1.5 millimeters), so a fairly thin wire. That might seem thin, but typically if you look at a wire, it has an insulating barrier around it, like a cylinder of insulation around it for kind of obvious reasons. And so this would just be, like, if you have a wire that thick, it's pretty small, but the conductor, like if we made a conductor with this diameter, if we put that insulation around it, that would make it, the wire itself, a little bigger. And yeah, copper wire. And let's say that the current in this wire is 650 milliamps. Oh yeah, what is an amp? Forgot, that's very important. We measure current in amps. So they were named after a guy named Ampere, who did some very important work on this subject, electricity and magnetism. So they named this unit after him. So an amp is a basic SI unit of current. And we can see from this equation, an amp is a coulomb per second. So charge in coulomb, time in seconds. I like to write that as an amp times a second is a coulomb, because then you can just divide them. But yeah, let's find the average velocity of the charges in this conductor, this copper wire. So we have to make a few assumptions. Now, in a copper wire, or just in conducting metal, kind of mentioned before, the actual moving charges are electrons. So we're going to consider this kind of still simplified model. Might need some room for the actual calculation, but so yeah, let's say we have a current. We have our wire that has a diameter d. So the area, like this cross-section area, so the area of a circle is pi r squared. R is d over 2. So the area is pi times the diameter squared over 4. And yeah, we have the diameter here. And a current of 650 milliamps. So let's, so what we're going to do is we're going to assume a picture like this. We have a current going to the right, and right now we're assuming that we have the electrons moving to the left. All moving with a nice constant speed v, and again, a very not realistic picture of what's actually happening. We're going to improve this picture a little bit by looking next at something called the Druid Model. But again, that's not perfect by any means either. Druid died in 1906. And yeah, I mean, this is a purely classical result. Quantum mechanics is not something that was just discovered one day. The very first work in quantum mechanics was in the year 1900, but it was one specific problem. That was blackbody radiation, which we talked about a little bit earlier. We're trying to explain the electromagnetic radiation emitted from an object. And a guy named Max Planck made the first step towards quantum mechanics by making an assumption about how energy is radiated. But again, in Planck's mind, what he did applied to this one particular problem. And the next step in quantum mechanics came in 1905. It was actually Einstein when he was describing something called the photoelectric effect. He came up with the idea of photons, which he said that kind of similar to Planck's idea, but he took it much farther. That light itself was quantized. Quantum theory. Quantum means just individual pieces. So instead of light being this continuous wave, as it was believed at the time, said it comes in discrete pieces called photons. And again, these quantum ideas were popping up. The next was looking at like a hydrogen atom, where a guy named Bohr came up with this idea that the momentum of an electron in orbit around the nucleus was quantized. He had no explanation as to why that was the case. And so again, it was kind of put together in pieces, and it was very successful. But a real kind of starting to develop a proper theory didn't come until the 1920s, with two people working independently. There was Schrödinger and Heisenberg. They both came up with different approaches that were in most ways equivalent to each other. Very different, but they gave the same results. And that was like where we can start to write down quantum theory in terms of like fundamental principles that apply to the universe, and not just kind of assumptions that had no real basis before. Like why an electron in an orbit can only have certain values of momentum. They had no explanation as to why, it just gave the right result. So they went with it. But anyways, so yeah, the Druid model is definitely pre-quantum. And explaining what's actually going on inside a metal, that is something that requires quantum mechanics. So we're starting with a very primitive model, then we'll go to something a little bit better, which is the Druid model. Still far from complete though. But let's go with this. We just want to find the drift velocity. Now, if we think about it before plugging in any numbers, we might expect these electrons to be moving very quickly. We have experience with small particles moving, namely like atoms or molecules in a gas, and they can move several hundred meters per second. And we also notice from our experience with gases that the lighter the object is, the faster it's moving. And an electron is very small compared to an atom. So we might expect that these electrons are moving very quickly. We're going to find out that is not at all the case. But let's do this. Let's find the velocity according to this very simple model, the velocity of these charges. So one assumption that we're going to make, which again, no explanation right now, really to explain this requires quantum mechanics. But copper, I wrote down a few things that we'll need here, like this is the mass density, like how many grams per cubic centimeter. And also here, like the atomic mass of copper is 63.546. So that means 1 mole of copper has a mass of 63.546 grams. But one other thing, it's atomic number 29. Let me write that down. So if you have a copper atom, the nucleus has 29 protons, and there's 29 electrons around it. However, that's just a single atom. When you put them together in a solid, every atom basically has 28 electrons that are fixed to the nucleus. They stay orbiting around that nucleus, but there's 1 electron that is free to roam around. And it's interesting, if you look at copper on an atomic level, or just solids in general, like crystals, like metals, they form these very nice periodic arrays, where like every atom has a place. There's different types of arrays they have. You can have like just a cubic array, where it's like, it's a 3-dimensional object. Or you have like hexagonal, there's all sorts of different shapes. But they form this nice array. And one thing that we've learned, this is a theoretical result, but if this array was perfect, like every atom was exactly where it's supposed to be, these electrons would be free to move with absolutely no resistance at all. So if you have an electron and you send it moving through this perfectly periodic array, where every atom is exactly where it's supposed to be, this electron will not lose energy. It'll just keep on flowing indefinitely. And but this kind of array doesn't actually exist in nature. It's actually impossible for something like that to exist in nature, where everything is fixed in place because of something called the uncertainty principle. You can never nail something down precisely to one actual location. So that's one reason why an array like this would be impossible. But another more down-to-earth reason that is temperature. We know that atoms move around. They vibrate. Like in a solid, these atoms are moving around. And the more energy they have, the more energetic these vibrations are. And so they can't be a perfect array if they're moving around. And so you might expect the higher temperature, the more resistance to motion that we would expect. And that's what we're going to find. We'll talk about that later in a separate video. Okay, so we're going to borrow this result, which is true to a very good approximation, that every atom gives up 1 electron that is free to move around. So we're trying to find this average velocity, and we can write down the result here. That'd be the current over n, little n, QA. And I'm going to... Now, we know that what's moving inside this conductor are electrons. So I'm replacing Q with E, because those are the moving charges. Each electron has a charge E, which I should probably write that down somewhere. So 1.6 times 10 to the minus 19 coulombs. Now we know the area. We know the diameter. We can find the area. We know E. We were given the current. What about M? Well, let's say we have 1 cubic centimeter. Just consider a volume of 1 cubic centimeter of copper. How many atoms will there be in 1 cubic centimeter? Well, 1 cubic centimeter would have a mass of 8.92 grams. Just the density is 8.92 grams per cubic centimeters. So to make life easy, let's say we have 1 cubic centimeter, we have 8.92 grams of copper. So how many atoms are there? Because if we know how many atoms there are, each one gives up 1 electron, so we know how many electrons there are that are free to move. Not how many electrons there are, but how many, they're called conducting electrons or conduction electrons. Those are the ones that are free to move around. And so here we know 1 mole is 63.546 grams. So the number of atoms is 8.92 grams times 1 mole over 63.546 grams, and then we multiply by Avogadro's number. So, let's see, this is roughly 9. We're going to get a number less than 1 here. So let's take 10 out of this. So let's do this. We have 8.92. Now let's take 10 out of here. Let's multiply by 60.2 times 10 to the 22nd power now. So we took 10 there. So we're going 10 to the 23rd is 10 times 10 to the 22nd. And that'll give us scientific notation now. So we're dividing by 63.546. I'll just cross off the units, they're easy enough to see in this case. And we're just getting a pure number. So let's do this, this fraction here. We have 8.92 times 60.2 divided by 63.546. So I'm getting 8.45 times 10 to the 22nd power. And so for copper, the number density of conducting electrons, I don't think I can fit that here. Let's write it here. This was given information. This is something we calculated. So yeah, this is how many conducting electrons in 1 cubic centimeter. So the number density is, that per cubic centimeter. And so now we have all of our pieces, and we can just plug in the numbers. So I'm going to erase this so that we have room. So let's plug everything in here. So this velocity that these electrons are moving, we have our current is 650 milliamps. We haven't talked too much about current yet. But I'm going to convert to amps. Milliamps are very frequently used in wires. So milli 10 to the minus 3, we'll put that on the bottom. Now here's our N value, which we just calculated. And that is per centimeter cubed. And the area is pi, let me do it this way. Pi d squared over 4. So instead of writing d squared here, let's do its own thing. D is 1.5 millimeters. Let's do it this way. Let's just convert to meters. So, yeah, we had millimeters. Mill is 10 to the minus 3, so we put that on top. Now, we also have this issue of centimeters. Let's say 100 centimeters is 1 meter. We're just converting everything to our base SI units. So we're getting rid of centimeters, millimeters, milliamps. We're just putting everything pure SI. And let's see what we have. Let's check the units first. Go right across. Oh, wait. Yeah, we want a velocity out of this. That's a bit of an issue. Oh, good thing we're paying attention to units. We're not done. This is N and A. We also need E, which is 1.6 times 10 to the minus 19th. So we put the 10 to the 19 on top. And now we want to eventually get a velocity in meters per second. So we have to get rid of these electric units like amps and coulombs. And we have a conversion factor here. An amp times a second is a coulomb. So just multiply that equation by a second. So an amp times a second is a coulomb. Now let's see what we have. Checking the units first. So area, or amp, centimeters cubed. I'm going to write that because we see we're going to cancel out that way. Here we have meters cubed. I'm going to write meters cubed as a meter times a meter squared. Because here we're going to have a meter squared cancel on the bottom. And then we have a coulomb. So amp, centimeters cubed, meters cubed, coulomb. That's all we've got on top. And then on bottom, we have meters squared, centimeters cubed, coulombs, amps, and seconds, which I'll just write down here. So now we're getting our velocity in meters per second. So the units worked out. So let's see if we have room to write this here. We have 650 times 4. So we took care of this, that, and now we have 10 to the 6, because, 10 to the third squared, 10 to the 6, times 10 to the 19. That's times 10 to the 25th power. Now on bottom, let's ignore the 10 to the whatever power for now. We have 8.45 pi. 1.5 squared is 2.25. And then we have 1.6. So again, let's check. We're ignoring 10 to whatever power for now. So 8.45 pi, 1.5 squared, and 1.6. Now 10 to the, here we have 3, 25. This is 31. So here, 100 cubed, this is 10 squared. Cubed, that's 10 to the 6. So yeah, and then here that'd be 10 to the 9 times 10 to the 22. That's 10 to the 31 power. And that would be in meters per second. So let's kind of clean this up a little bit. 650 times 4. Let's look at the number part. Should just do this one in my head. That's a nice easy one, but 2600. And let's look at the bottom. 8.45 times pi times 2.25 times 1.6. On bottom, I'm getting 95.57. So, and then we have times 10 to the minus 6. So let's divide. 2600 divided by 95.57, getting around a velocity of 27.2 times 10 to the minus 6 meters per second, which is extremely slow. Okay, now why is that? Well, it's because this is not at all a good model of what's happening inside a conductor. Now, the electrons inside a conductor typically move around 10 to the 6 power meters per second. That's, the speed of light is 3 times 10 to the 8th. So 10 to the 6, that's a million meters per second. That's how fast electrons in a conductor are typically moving. So this velocity completely off. However, it's a bad model. Still kind of useful to look at. But let's look at a slightly better model called the Druid Model.